the previous lectures you have been considering the CPU cache memory interaction. So, I can, as you can see here, now cache is between CPU and memory, okay. And we have not really completed our discussion on cache, we will continue. But then at this point in time I will digress a little and take up the next issue also, because these are the issues are similar and the techniques also will be similar. Okay. Now, why? Just like cache is between CPU and memory and acts as an intermediate thing, you can see that memory is intermediate between cache and store, and so we can also consider, let us say, memory as a cache between store and cache. Of course, memory as a cache, when we say cache with an inverted comma, okay, is it not? Like this is in between. Now, we find this memory is also as in between this cache and store, right. So, for the moment we will also take a look at the issues on this end, right. We have been considering this particular one, and it so happens that historically the cache development and then the other development related to memory storage had been say they had different roots actually. And so, what happened, some of the terminologies functionally they are same, but then as far as the terms are concerned they are slightly different, we will see that too. Now, before that I would like to go back a little and then take a look at the 3 factors. Remember, I was always talking about in the memory hierarchy the speed, cost and size. So, this also we must have in mind when we are discussing these issues. Okay. Now, I will just give some typical figures, right. So, it is only really typical, and we should not think that this is the figure. Okay. We may say it is the order of, okay, you are familiar with that, right. Now, speed, if you just take cache, okay, for a particular unit, that is all these things you must relate to some specific unit. For instance, if the speed about the cache we take it as 20 nanoseconds, okay, that is basically it is a memory access time for a word, okay, maybe a byte or whatever. Now, the similar figure in the case of the memory, see, will be of the order of say 100 nanoseconds. Though said 100 can as well be 200 or sometimes even less. Okay. Whereas, in the case of storage essentially magnetic, it takes a long time, say 10 to 20 milliseconds. So, I will just put it as 20 milliseconds. Now, you can just see here, this is nanosecond, this is also nanosecond, sometimes this can go to microsecond, that is very old technology, but then this one you can see vividly different, millisecond, right. And then the cost of it, again as I said, for a specific unit, suppose for a specific unit it may be chip or whatever size that you may consider. So, let us say in terms of dollar, if we say we have to spend $100 for a particular unit size, the main memory would just cost about $25. You see, it is at least 4 times cheaper. Now, in the case of magnetic store, it may be as low as $1, fine. Now, you can see that why we had in fact had to introduce the hierarchy, right. If you want to go for a very cheap one, you may, but then you pay at you pay in terms of the speed, right. It is going to be very slow. Then the size again, typically if the cache size is about say 16 KB, that is 16 kilobytes assuming, can of course be different. Now, you can talk about an 8 to 16 megabytes, let us say. It's really a good system will have say about 8 to 16 megabytes, especially of late, and storage say the size will be about say 1 gigabytes. Of course, it can also be quite a few megabytes, hundreds of megabytes we may say, okay, gigabyte. Now, let us have this in mind Okay, some of these figures we will keep referring to, because while discussing the issues here, we will see there are also issues here, they are related, but then these factors will come into play. We will talk about it, fine. So, as I already said, we can look at memory as a cache in between store. Then what is the difference between the cache and the memory? We were calling it as DRAM. In general, you may call this as a main memory, okay? Main memory, normally it is a DRAM subsystem. Good. Now, what does cache hold and what does the main memory hold? We knew that cache consists of blocks of data. Okay, block can be variable size, it may be a single word, multi-word, we saw both the cases, right. Fine. And what does cache hold? Cache always holds something which the CPU wants as as frequently as possible, as necessary, and as quickly as possible. These are two things. So, while a program is executed, we find that adjacent instructions, right, will be the probability of accessing the adjacent instructions is going to be very high. So, you would find most of them in the cache or the data, it depends on the organization of the data. Okay. So, we can always say that cache holds the active portions of a program, agreed. Cache holds active in the sense the one which will be used or acted upon by the CPU, okay, that portions of a program the cache holds. So, remember portions of a program, good, that is a program is executed, it consists of instructions and data, the adjacent instructions, the adjacent data, okay, neighboring location. Remember the principle of locality, something which is locally available, right. So, there is always a very high chance that the ones that are locally positioned, okay, instruction or data is going to be required by the CPU as frequently as possible, and of course, to see that the CPU utilization, okay, processor utilization is the highest, we tend to put whatever is going to be required as frequently as possible, also accessed by CPU as quick as possible, that is going for say these units or the chips, okay, which will respond very fast, right, good. So, the blocks actually contain portions of the program. So, they are going to be used by the CPU. Now, what will be the memory hold? What will be the memory holding? Okay. Now, if you say cache holds active portions of a program, we can say that the main memory holds active programs. In what sense? Assuming the storage has multiple programs, maybe programs of different users. Okay. So, we can say that the main memory, okay, this holds active programs. What do we mean by that? There can be possibly active programs. Now, of course, when we talk about active programs, what we have in mind is the multi programs or the so called multi programming, okay, situation. That is what we have in mind, agreed. So, historically the issues here came up when multi programming was needed. Now, why do we say that? Because today we are all familiar with the desktop PCs, and possibly you would be the only user and you may be running only one program, right. But historically it was not so. We had essentially mainframe computers in computer centers, right, mainframe computers, even today you may still have in big establishments, right. And it is possible that there are many users, right, and so the multiple programs are there, that is the multi-programming feature is still a necessity. It is possible that the CPU is a very special kind of CPU which is running very fast, okay, and possibly something like what you are thinking of is a highly parallel programming system, in which case you do not talk about a single processor, okay. And when you invest so heavily in systems, then you would like to see that it is used as okay, it is used as well as possible, right. That is the utilization factor must go up, in which case you accommodate multiple users. So, the situation is still there, but nevertheless this is true only in the case of multi programs, right. So, you can see that historically there was a necessity for allowing multiple programs, and also again in those days these memories were costly. In other words, all these things like memory as a resource, if you look at it, would be looked at as a scarce resource, okay, mainly because it was costly. I am still talking about historical condition, okay. So, we can refer to them as scarce resource, and so you can see that multiple programs will have to be accommodated, and it is possible that when we talk about multiple programs, let us just assume multiple users, right. So, it is possible that one user program, when it is taken up, the program cannot be completely executed, there may be some problem, right, in which case that program will have to be program execution will have to be stopped, or what we call as aborted, and then that has and then another program must be taken. This is one situation. Another thing is there can be some programs which may consist of many say routines, and one routine may call another routine. For instance, you may be having a lot of CPU bound process or program, and that may say lead to, let me call for IO routine, and IO routines need not really be taken care of by the main processor. So, there may be a separate channel processors for that, in which case temporarily this main processor is relieved from that particular activity, and so while waiting for that IO process to be completed, the CPU can take another program and proceed. Okay. This is one situation. Another thing is, it is possible that the application is such that the program is really huge in size, right, and we may be able to store the entire program on in the storage unit, but the entire portion of the program we are not able to bring it into the main memory. So, this is a situation even now, okay, possible. It all depends on the application, in which case only some portion of the program itself may be brought, very much like cache, but then it is a different situation. Okay. That is, we are talking about a large program, okay, consisting of multiple routines, or generally referred to as multiple tasks. Okay. So, then what we would have is, we may not have the entire thing running, we may be having only a part of the program in terms of so many tasks. Okay. Good. In which case, how in addition to this, in case the memory is costly, right, then the only solution is have as much of storage as possible, and whenever required bring the portion of the memory to the main memory, the size of which you keep it as low, because it is costly, okay, as low as possible, so that you bring only chunks, right. So, you can see here, whereas here we were talking about the blocks of data coming from the main memory, here we will also talk about chunks of programs coming in here, right. Good. So, you can see that Historically multiprogramming was the issue, mainly because of the mainframes, and so we had a problem about allocating the scarce resource, okay, allocating scarce resource to different programs. This was one problem, and this of course specifically for mainframe situations. Okay. Now, today the situation is somewhat different. Now, this is one issue, let us say. Today the situation is somewhat different. What is it? It is like this: the CPU has become very powerful, the CPU word size has increased from something like say 8 bit, 16 bit to 32 bit, 64, and now it is going to 128 bit. Now, what happens? The address size that also keeps increasing, the number of bits address from 16 to 20. Now, remember, 1 bit extra in address is going to double the size of the memory, right. If with 16 bit memory address, 16 bit address, we have 2 to the power 16, that is 64 kilobytes. If it is just 1 bit extra, 17 is going to be 128 kilobytes, that is double, right. So, 1 bit in the address size is going to increase a lot. Now, when we talk about the CPU's addressability increasing, and one small bit in this is going to double the memory size. So, what happens is possible we do have this situation now. There is it is possible that CPU's addressability is very high, but then we are not able to have that much of memory, physical memory. Okay. Mainly because if you want to have, you can just add 1 bit to this, and that is not going to cost more, but then 1 bit means double the size of the memory, total address space is going to be double, and we are not able to have, in which case again we have got to see, and this storage being cheaper, there may not be problem about having that. So, what we may have is the CPU's addressability has increased, and the user may be told, okay, 20 bits fine, 2 to the power 20, right, that is 1 gigabyte, right. So, that is available, let us say, but then it is possible that 1 gigabyte memory you do not have, but then you have only 16 megabyte, let us say. Then again we have the same situation. Now, this of course is currently this is possible, right, that is the CPU's addressability has gone up, and so the program size can go, that is from the user point of view, but from system implementation point of view we cannot populate the total address space, right. So, in which case the user may be told, fine, the CPU has larger addressability, and so the address space has increased from programming point of view, but physically speaking the memory size is less. The user need not be told, okay. The user may just be given an impression that now he can have very large program, and then it is up to the designer to see that the large program is brought in chunks and then executed here, fine. So, in other words, what we are doing here, now this is the situation, CPU has larger addressability, right, that comes about because of the number of address bits addressability, okay. That is the total address space, that is from the user point of view, right, the total address space has become in fact has increased. This is from the user point of view, but physically the memory is not going to have that much. In other words, the user is sort of told, fine, you have a large address space, that is he is given an impression that the address space is high, but then physically speaking the address space is low. Now, who is bothered about this physical address space? The one who has to run the program, not the one who has to write the program, right. So, these are two things. The user writes the program and he will be told fine, you have large address space. So, let us say 1 gigabyte is available or more, whatever, okay, or even 0.5 gigabyte is available. But then when it comes to the physical this thing, it is less. Okay. So, this is a situation and that has brought in two kinds of address space, that is the total address space being high is indicated to the user, and this particular thing is called the virtual address space, okay, the virtual address space. But in the system, okay, in the system what we have is what is physically available, right. So, the physical address space is restricted, okay. The physical address space is less. So, now, but the user is not really concerned with this, the user is only concerned with this particular one. And so, this virtual address space that is from the user point of view, he has large address space, but it is not physically existing, that is what it means. Okay. And so, from programming, since programming point of view this exists, this particular virtual address space is also called logical address space. Okay. It is also called logical address space, mainly because from the user or programming point of view this space is available, but in reality it is available where? It is available in the storage. Okay. But in reality for the CPU to access and get it, that is not available, because that is going to be restricted by the main memory size what is possible with given the cost and other consideration. Okay. Now, what will happen in case this is made physically available to the CPU? This is the problem. This CPU which can really run at 20 nanosecond, let us say, will have to run at 20 millisecond, you will see that. So, the CPU utilization comes down, fine. Now, it is because of this particular thing we are talking about hierarchy also incidentally, we are talking about the hierarchy mainly because of this, fine. Now, let us proceed with this, that is, though historically multi-programming had brought in certain issues, the issues are still valid though from different point of view now, okay, presently, good. Now, this means the user writes his program assuming large address space, and while running the program this virtual address must be translated into physical address space. So, we talk about address translation and from what? From the virtual to the physical address. Now, this is one. This is also called memory mapping. Why? Because you have to map the virtual address space to the physical address space. Okay? Memory mapping, this mapping this particular address to this. Of course, memory mapping is a term used in some other context also, we will talk about it later. Okay? Good. Now, what about this multiple programs we are talking about here, right? Multiple programs, oh I did not write here, but anyway, multiple programs. Does the situation exist now? It does. From what point of view? Mainly because software complexity has increased. What we are doing is today we from the user point of view we talk about application programs. The one, because user is essentially concerned with writing a program for a specific application, okay? And the software complexity has increased so much. So, from the system point of view, okay, from the system point of view we talk about system programs or system software, right? System programs or the system software, that is we have system software and we have the application software. So, at least user programs are there, system programs are there. Agreed? Well, essentially the user is running this program and this is going to be run under the care and supervision of this program, is it not? So, we still have the two things, that is you have both user programs, this is one type, and then we have the system programs, this is another type. So, still the situation of multi-programming exists, but it is from a different point of view, right, because under the care of this is going to be run. Good. So, at least system, or generally we talk about an operating system, okay. This is one thing, and then the user or the application. So, certainly these two types of programs are there, and there should not be confusion between one and the other. In other words, there will be some portion of the memory which will be used by the system and some portion of the memory used by the user or the application, fine. Now, the respective programs must be stored in separate spaces, so that there will not be any confusion, otherwise what will happen? Okay. It is something like a doctor and a patient, right. Now, what happens if the patient becomes the doctor? Because when doctor becomes the patient, he comes there, but when the patient becomes the doctor, what will happen, right. So, that confusion should not be there. The same thing here too. So, essentially we still have to make sure that in the case of multiple programs, the respective types of programs are compiled and put in separate spaces. Okay. So, there is the need to compile, that is generally the software is written at very high level. So, they must be translated or compiled to lower level programs, lower level codes which can be run by the hardware, right. So, to compile each program, now here we are talking about the system program and the user program, or system software and the user software. We have to compile each program in its own address space, that is they must be isolated, otherwise there may be some problem. That is what we are talking about when we say in its own address space. What we are now talking about is the protection that must be offered between the two types of programs. One should not corrupt the other. Certainly, the user program should not corrupt the system programs. So, you can see here there are two things. One is we need virtual to physical translation. Okay. The other thing is we need to protect the appropriate segments of software, that is user or system appropriate, right. Good. So, it is not that the though historically something would have started, still these issues are very much relevant even in present day situation. So, now we will be having the logical or virtual addresses here, and we will be having the physical addresses here. Okay. So, it is possible that we have different programs, at least user program and system program minimum, one user. There can be multiple user, then we talk about multi programs. Okay. Now, system program will be here, user program here. A core of system program must always be available, and the appropriate portions of the user programs may be brought in depending on the storage memory size consideration, right. And at any time the cache will have the part of the program, right, which CPU can access as frequently and as quickly as possible, so that the utilization of the CPU may be high, fine. So, this holds the active programs main memory all the programs are available in storage. Okay. All the programs that are necessary are available in storage. Main memory holds the active programs, cache holds the active portions of a given program, and what does CPU hold? CPU holds usually a portion of one instruction of a program, okay, nothing more, and specifically in one state of the CPU, what is it? In one state of the CPU, it is a simple register transfer level activity. Fine, you are able to see the relation between these. So, CPU goes through instruction after instruction, that is instruction cycle. The instruction cycle ultimately consists of states, and cache a portion of a program, memory those programs which are to be run, and storage all the things that the system must be having. Fine. Now, CPU looks for something in the cache. If it is not available, we say fine, why do not we look at positively? When it is available, we say the CPU has hit. If it is not available, we talk about a miss. Now, whatever is not available there, it has to fetch from the main memory. What does it fetch? It fetches a block, because cache is defined in terms of blocks of data, okay, which the CPU may access. So, whatever be the size of the block that it may have to bring. Now, similarly, between main memory and storage, okay, now storage is going to have very large address space. So, lot of locations, we think in terms of some location, address locations, whereas the main memory is what is going to accommodate whatever is physically possible. So, this in fact is a subset of this, is it not? This is less in size, this is larger in size, this is a superset. So, similarly, whatever the CPU needs, if it is not available in main memory, it has got to be fetched from here. So, here again we can talk about similar to the cache hit and miss, here also we can talk about, that is something whatever the CPU requires available or it is not available. Now, the problem is this, look at the timing. If something is not available in cache, at a penalty of 5 times the time duration given, you can get it 5 or maybe a little more, but then look at this and this. If something is not available in the main memory, okay, which the CPU could have access in 100 nanoseconds, now it is going to access in 20 milliseconds, milli. It is nano 10 to the power minus 9, this is 10 to the power minus 3. So, a factor of 10 to the power 6, a million. So, if something is not available here, getting it from storage is going to be cost hundreds or thousands of clocks as far as the CPU is concerned, whereas here it may be tens or possibly a few hundred clocks. But then, so the penalty in case something is not available here, to get it from the storage is going to be very heavy, and so that situation must be avoided. That is why we say the memory must hold active programs, that is whatever that is needed for executing a program, that must be made available. The only situation when it cannot be is when the program is very huge in size. Okay. Now, talking about this cache and the main memory, let us also look at the terms, how they have come about. You had sort of seen the similarity, correct, but then the terminologies are different, again historical reason. Okay. Now, in the case of cache, we were talking about a block of data, okay, maybe I will put it like this, the cache and then the main memory. Okay. Now, in the case of cache, we were talking about a block of data. Okay. Now, similar to block of data, in the case of memory, we have what is known as page. Here also it is similar to block of data, okay, it is called a page. In the case of cache, we are talking about in case it is not available, there is a miss. In the case of memory, we call it as a fault. Okay. So, in this we will be talking about a cache miss, here we will be talking about a page fault. Otherwise, they are similar. So, really we have not looked into some details of cache, because in this memory to storage also, okay, the issues are similar, and after we study something about this memory to storage interaction, that is this part, okay, memory to storage, we will come back and discuss and continue our discussion the cache. Okay. Now, what is this cache and memory and other things? So, we really have to work out and go into the details of how this virtual to physical address space, okay, this translation or relationship holds good. So, we have to draw a few more diagrams. We are talking about the virtual address space essentially created by the CPU's addressability, and the physical address space essentially what is physically implemented, that is the memory part. Okay. Now, we may say that this virtual address space is a storage space, is it not? Because essentially it is also disk address space. You can have anything that you want in the disk, only thing what we can have in the memory gets restricted. Okay. So, we will start with a few figures, assuming we have a system with memory of size 64 kilobytes, okay, 64 kilobytes, and so that is the total the size of the physical address space 64 KB, right. Suppose we have the CPU of 20 bit address, which generates a 20 bit address, then what does it mean? That is 2 to the power 20, which is 1 gigabyte, right. So, this in fact is the total address space which we may call, which is virtual address space. Now, when the CPU supports 20 bit address, the user is going to assume that the address is of 20 bit, and so he is given the impression that 1 gigabyte space is available. So, the program is going to consist of 20 bit address, that is going to be the size, but whereas physically the system designer has included only memory of 64 KB. Now, this whatever address that is generated by the program will have to be translated. Okay. Now, again we have to just recall what happened historically. In those days, the job of translating this virtual to physical address, okay, this particular thing was sort of left to the users. In other words, the total program will be sliced into some chunks which can be loaded at any one time into the memory, and those things those chunks of program, or we will just say they were called actually overlays, memory overlays. In other words, I hope this conveys the impression that the user looks into the program, and if the program is of very large size, then he splits into portions of the program which are mutually exclusive, in other words which can be run independently. Okay. So, just overlays or memory overlays. So, these things were left to the user. Now, in other words, the user was burdened with the additional responsibility of looking into the program, splitting and organizing and all those things. Now, these days the operating system will look into those things. In other words, there must be the appropriate hardware software support which will talk about the translation, protection, all those things whatever we talked about. Okay. So, historically it was left to them. Now, is it not? What is the meaning of software? Software essentially is one which softens the whole system to the user, right. if the user is burdened to create overlays and then load them appropriately, not only creating overlays which are mutually exclusive portions of program, also loading them into appropriate time, when exactly to remove and when exactly to load, all these things were left. Agreed. Now, these days the system software takes care of it, okay, fine. And remember, this has absolutely nothing to do with the application part, that is a user is essentially concerned with the application program, not this kind of system thing, okay, system, whatever the system has got to do, fine, good. Now, let us go. We said memory 64 KB. Now, what is that? That would mean essentially we are going to have a 16-bit physical address, that is because 64 KB is 2 to the power 16. So, we are talking about a 16-bit physical address and a 20-bit virtual address, correct, fine. Now, we were talking about pages, is it not? What is a page? We said in the case of cache, we are talking about a block, a portion, right, which is always available. Now, similarly, in the case of this one, physical memory, right, we talk about a page consisting of say 1 KB or 2 KB or whatever be the size. So, we will just assume that the memory, this is the total address space. Suppose this is split into we just okay, arbitrarily take, suppose we have 16 pages, okay. Basically what we mean, we have 64 KB, so 16 pages each of 4 KB. So, this is our page size, right. So, 4 KB is our page size. So, what we are talking about is see, this is in disk and this is in main memory, right. The transfer between the main memory and storage takes place in such a way that the whole page of data information in general is transferred between these. Like we were talking about a block, here we are talking about a page, okay. So, we have just assumed arbitrarily that the page size is 4 KB, meaning any time 4 KB, whether for that particular program 4 KB is required or not, enough or not, that is not the situation, okay. Maybe 4 KB is not enough, the program size is 16 KB, in which case we talk about the program consists of 4 pages. Maybe the program size itself is only 1 KB, in which case 4 KB is still transferred, right. So, that is what it is. So, what is transferred between the storage, that is the disk space, and the memory, that is the DRAM space, okay, that is of size 4 KB. Okay. Always remember that this transfer is going to take a lot of time compared with DRAM or main memory to cache. Okay. So, from that point of view, it is always better to have the page size as large as possible, because in one go everything can be transferred, but of course, there are other things. Now, so we talk about 4 KB pages, okay, which means we have here essentially 16 pages, right, because 4 KB and 64 KB. So, let us say if this is page, normally we start with page number 0, but we will say 1 because we can easily follow that way. This is first page, this is the second page and so on. Then we have 16 pages here, okay, 16 pages, that is what we have here. And it is of course meaningful, this is also a page, okay. Now, it is also meaningful to split the disk space also into the same size of pages, because the same chunk is going to be transferred. So, what about here? Here we will be having how many? We can work it out, okay. Here also each one we can talk about, for instance, this is page number 1 and then appropriately the page, okay. That is basically 1 gigabyte divided by 4 KB, that will give the number of pages. We will work it out. When we take the address, automatically this will come, fine. Now, you can see here a few more terms I would refer to before I proceed, because in literature the different terms are used. For instance, in some books you may find this as referred this being referred to as virtual page, okay. That is, this has so many virtual pages, and whatever you have here, this will be referred to as physical pages, okay. Now this is one thing, this is one term. In some other literature, a page is always only a virtual page, and what you have in the memory will be called a page frame. I hope you can understand why it is. That is, essentially it says here you have so many, say 16 frames into which this data will be, these pages will be fitted in, okay. So, I think we will follow this term, that is, we will keep calling this as physical page and keep calling this as virtual page, okay, because there are some variations. So, you may find page and page frame, this is also another term, or virtual page and physical page. We will follow this physical page, fine. Now, let us see one more thing. Now, maybe I would specify that this particular thing will have 256 pages overall, okay. We will work it out. Now, this means essentially from the address we will see, okay. Now, you can take it for granted, there will be only 16 physical pages and we have 256 virtual pages for this initial assumption. Now, this means at any time we can have physically only 16 out of the total 256 pages. It is not a very good figure actually. What happens? It is possible that quite often the page that is needed is not at all available there, because between 16 and 256 you can see it is not very good, but just we have started with some figure, we will continue, okay, fine. At any time only 16 of the 256 pages will be available in the physical memory. Now, there must be information on which 16, this is number 1, okay. Only 16 of 256 pages are available in the physical memory, okay. I will call that is main memory. Now, there must be information of which 16, this is one thing, this information must be available somewhere, right. And another thing is there any necessity that page 1 must go only into page 1? No, it is not meaningful, okay. To make it quite universal, what we would say is any virtual page can go into any physical page, okay. That way the efficiency can go up, okay. If you bring in any restriction, there will be problem, right. Of course, there may be problem even otherwise, we will not worry about that. So, if you say that any page can go into any page, we need to have that information also. So, number 1 is which 16 of 256 pages, then among these 16, okay, where each of these 16 pages, okay. This information also must be available somewhere, right. Now, you can just see when we are trying to solve the issues of timing and then giving the user say this kind of a virtual addressability, then we have to worry about maintaining some extra accounting information. In other words, these are all overheads, no, they are not really contributing to the actual processing, okay. This particular thing we will continue in the next lecture, talking with starting with a 20-bit address and then going in for a 16-bit address, and then remembering the need for maintaining this information.